Hello and welcome. In this video, we'll be discussing some more of the specifics about the namesake for this lecture set, simple linear regression. We'll kind of talk about what even is this thing and how can we use it a little bit. So correlation provides a useful tool for looking at relationship between, remember, two continuous variables. But there's another option that's better in almost every way. It provides more detail in the relationship. It allows us to do more things with our model, such as predict. It still lets us test the degree of relationship and calculate the proportion of variance in one variable explained by the other. And it's just as easy to calculate, or maybe even easier. So this method is called regression. And for me, when we take this as the broader category, that is not just this lecture set in simple regression, but the next one we'll talk about too, this really is Pandora's box. It opens up so much in terms of the analytical world, and it really invites a lot more creativity to the table than we've thus far been able to take into account. Again, the questions become more about the theory, the background, not math theory, but like the theory of the problem. Well, if I'm doing marketing, what else do I need to consider, etc.? We talk more about interpretations. All right, well, if I get to make this interpretation in light of that, is that a good thing or a bad thing? And then we talk a lot more about context of interpretations. We really focus on figuring out how do we use this stuff, much more than how do we calculate this stuff. And because of that, again, it's just a lot more interesting. As I mentioned in a previous video, that's what I do professionally. That's why I enjoy it. I'm not a huge fan of the manual, tedious hand calculations. I'm much more of a fan of the creative, innovative solutions and thinking about problems in new ways that lead to better conclusions and more informed decisions. So there's a bunch of types of regression. And again, in this course, we're going to talk about two. I've mentioned them, but here we'll present them formally. Simple linear regression is a regression that involves one dependent variable and one independent variable. X, usually what we're using for our independent variable, Y for our dependent variable. In the next lecture set, we're going to talk about a concept called multiple linear regression that allows us to have multiple independent variables. I'm not going to go too in depth on that because, again, we're going to have a whole lecture set discussing it. But that's the contrast. So in our case, when we say simple linear regression or SLR, we're not calling the analysis simple or anything like that. We're just saying that this is the regression that only includes one independent variable at a time. So again, correlation looks to measure the strength of the relationship, but regression talks more specifically about how does X and Y relate to one another. So with correlation, we looked at the cloud, but with regression, at least in the default regression and the basic simple linear regression equation, we look at the line. We look at the slope of the line, we look at the intercept of the line, etc. Because of this, it's actually more important now to make sure if I have an independent variable and a dependent variable that they're denoted correctly. So with correlation, it didn't really matter which one was which, but in regression, it is important to make sure the independent variable is listed as X and the dependent variable is listed as Y. So in a simple linear regression, we'll use ordinary least squares with a single explanatory independent variable and a single response variable, which have a linear relationship. Love that. So a couple key points to pull out. Linear relationship. So as with the Pearson's correlation coefficient, when we're talking about a simple linear regression, we're looking at linear relationships only. First point. Second point, with simple linear regression, again, the simple part simply means we're looking at a single independent variable, 1x. Last but not least, this ordinary least squares thing pops up. You'll see it denoted OLS. And we'll talk about it, but essentially what that means is we use the sum of squares as a measure of variability that we're trying to deal with. So when we think about what this means, the goal is to put data on a graph and draw a line that best fits it. So a line, linear, single explanatory variable. So it's just a two-dimensional graph, one X, one Y. And then best fits the data. Well, if you're wondering what that OLS thing does, in a description of the technical sense, the ordinary least squares defines what is the best fit. So different people could have different distinctions of the best fit. For us, we'll look at the squared amount of the distance between our line and all the data points, and we want the line that is the closest distance in terms of the squared difference between our line and the data points. That's what OLS is. It says that's how we're defining the best line, is the line that's the closest to the data points in terms of the sum of squares of the errors. And I just used the term sum of squared error, epic foreshadowing, but that's also an epic pre-shadowing, I don't know, post-shadowing. We talked about that. We talked about sum of squared errors in the ANOVA context, and this is the exact same thing. All right, so we'll talk about the method of doing that in a moment, but first let's skip ahead a second to say we're eventually going to get the equation of a line. So ultimately, again, we're looking for a line that best fits our data. And so eventually we're going to end up with a line. And again, that OLS minimizing the squared errors between our line and the data. We want as little error as possible when we square them and add them up. Now, when we talk about the equation for a line, this is exactly the same equation for a line as you saw in maybe high school. I guess in high school you had, I don't know, point slope form and blah, blah, blah form and slope intercept form and whatever. I don't really remember all the forms. I think this one's slope intercept form, but this is the only form we're ever going to use in this course. And as far as I'm concerned, you can forget about all the other forms. So I'm sure a mathematician going to hate me for saying that, but yeah, this is the only one that we're going to use, is the one that has the slope and the intercept, because that's the information we're interested in at a practical level for using these results in a meaningful way. I will mention that while we're using that same y equals mx plus b, we are going to rename the variables slightly. The slope was previously named m in the y equals mx plus b, but now we're going to call it beta 1 for the population value, or b1 for the sample value. You'll also see the notation beta 1, that is the population value, with a little hat on top. And it'll be important to remember the hat notation. I actually quite like the hat notation, so you'll see that appear every once in a while. The hat notation is where I just use the population notation, and then I put a hat on top to mean the sample thing for that. So B1, the sample slope, and beta 1 hat are actually representing the same thing. Both are representing the slope calculated from the sample. For the y-intercept, we used to call that lowercase b, and I know that's a bit confusing, but again, that old high school math notation, that's just really not going to stick in statistics. The new notation that I'm describing is very, very common, and it's the only notation you're going to see. So I need to be careful about that. It is far and away the standard notation for regression that you're going to see. The y equals mx plus b is not it. So anyway, we're getting rid of the b for the y-intercept, and instead we're now calling that beta 0 for the population value, or b0 or beta 0 hat for the sample value. And again, population versus sample. Population is what's the line if I calculate it for all of the data points in the population. Sample is what's the line if I calculate the best fit line based on my sample data set. I mentioned the hat notation already, but do make a note of it. It indicates, again, an estimate or best guess for that value. So it's for beta 0 hat, it's the sample best guess for beta 0. And I'm going to keep using that. So for example, a quick example of how I'm going to use it, we're not going to talk in detail about the equation. This equation we're going to talk about in a second, but y hat equals b0 plus b1x. So that is the best guess for y. Another way of saying that we'll talk about later is the predicted y is my sample intercept plus my sample slope times x. So that's a way that we'll see that is best guess hat, best guess. And again, for y, sometimes we'll call that predicted value. For the betas, sometimes we'll call that our sample estimate. But that hat notation just means our best guess. All right, so it is important to realize when we're talking about doing a line, a best fit line to real data. This is in an applied social situation or social research situation or business research or whatever else you want. A research situation. The lines aren't perfect. They're never perfect, right? So there's no way to draw a perfect line that goes through every dot. We could draw a bunch of squiggles, but there's some problems with that maybe we'll talk about in the end of the next chapter, but maybe we won't even talk about them. But if I'm just trying to draw a single line, it's just impossible to go through every dot. So the goal is to do the best we can, but we have to realize then that even in the best possible line, it's not going to hit every dot. It's just going to be as close as possible to them. So because of that, we have to just acknowledge that exists. In fact, we'll introduce a quantity or a term for the difference between the dot and even the best line. So the idea is that the difference between the dots and the perfect line is called the error. But remember, we're never going to have the perfect population, perfect line. We're just going to have our best guess from the sample. So the difference between the dot and the best guess line from the sample is called the residual. And so we're going to use both of these terms. One way to think about this is you can think about the residual as being the sample version of error and the error being the population version of error. The population version of error will typically denote as this epsilon character. And I don't have it here, but if you want to jot it down, we'll introduce it later. But the sample notation or the notation for residuals usually uses an E. If you haven't figured it out yet, we use Greek a lot for population, and we use the Latin characters for sample values. So E, epsilon for error. We have the Greek version for the population, and we have the Latin version for the sample. So epsilon for population error and E for the residuals or the sample error. All right. Good terminology to know because we're going to come back and we're going to use residuals all the time. And whenever I say residual, again, I want you to think the observed errors or the errors in the sample. All right. But now that we have this idea, here's the deal. Again, we have our best fit line, but data points aren't perfectly going to fall in the best fit line. So if I want to have my Y values, I have to acknowledge that there's going to be a bit of error associated with this. So here's what I want you to look at in this equation. Do I have it written out here? All right, I don't. So here's what I want you to look at in this equation. We have two components. This component is essentially the line. So I've got my line, and then in addition to the line, to find the exact height of the point, I have to add the error. So if I have my perfect line, that is my line using betas, then I add epsilon, that is my population error, the distance between the point and the perfect line, and that's my height of that particular data point. So Y in our graph, X is the horizontal axis, Y is the vertical. So if I'm looking for the vertical height given an X value, I go to my X value, and then I go up to my line, and so that's a big chunk of it, that line piece, and then I have to move a little bit up or down depending on if the data point is a little higher or a little lower than the line. That's the epsilon piece. So every line or every dot that I observe, that is my YIs, the actual data that I see, every dot is going to be a little bit off the line, and it's got two components. It's got the line component and then the error, which is essentially the adjustment for that particular dot above and below. I also want to know which variables, or note which variables have a sub I and what that means. So sub I simply indicates that each individual has their own. So let's read through this equation and see which variables have sub i's. So I see Y, and remember what Y is. That's the dependent variable. The dependent variable has a sub I. So depending on the example, previous example we used was the profit. We said, I think the marketing budget influences the profit. So Y would be the profit. And each campaign has its own profit value, or each person has their own. If we're doing weight and height, each person has their own, say, weight. Beta 0 and beta 1 don't have a sub I. So let's go to the next one that does, X sub I. Well, each observation has its own X value. So every person has their own Y value and their own X value that we observed from the data. Okay, well, that kind of makes sense. It's almost stupidly obvious. That's okay. That's good. We like stupid, obvious things. Every person has their own X and Y value. You'll also notice the epsilon has a sub I. That is, every data point has its own little custom distance from the best fit line. So each person has three things: their X and Y, which were given at the start of the problem. And then after we fit a best line, there's a little bit of error associated because the line didn't perfectly go through that data point. And there's the distance between that point and the line, and that's that epsilon when we're looking at the population values, or if we're looking at the sample values, it'll be E. All right, so that's which ones have an I, and hopefully that makes a little bit of sense that every person has the X and Y values given at the start of the problem, and then after we work a little bit and fit our best line, because the line's not going to be perfect, every person's going to have their own distance by which that line was wrong for them. Okay. Notice what doesn't have a sub I. B0 and B1, or beta 0 and beta 1. Beta 0 is the intercept, and beta 1 is the slope. What does this mean? This means that the intercept and slope, essentially the components of the line, are the same for everyone. So while everyone has their own X and Y values, and everyone has their own amount that the line was off, everyone doesn't have their own line. We use one line to represent all of the people simultaneously. And that's where we talk about these average predictions and stuff like that. It's because we kind of average everybody into a single best guess line. So everybody has their own dot, and once we do the best guess line, everybody has their own distance from it by which that line was wrong for them. But we use a single line for everybody. That beta 0, beta 1, no sub I, indicating it's a single line for everyone. All right, so let's graph this out a little bit. I think this will help to explain some of the different concepts that we just talked about in the equation form. All right, so we have our points, and these are our X, Y pairs. So this is my X sub I, Y sub I for each person. So for instance, in that very, very bottom dot right above the marketing budget, 7, I might have X sub I, the marketing budget, the one that's on the horizontal axis, is about 7. And Y sub I, gosh, it's hard to see here, but it looks kind of close to 0, like maybe 0.2 or something like that. So if that's the first data point, it'd be X sub 1 and Y sub 1. It's just the X value and Y value for the first individual. And that's 7,000 or just under 7,000 and close to 0, maybe 0.2 would be my pair. Again, just under 7,000 X, Y is around 0.2. All right. Hopefully we're all cool here, where our scatter plot dots come from. All right, now we have our line, and this is our best guess line. And again, we're going to use some math. We haven't really talked about this, but we're going to use some math to find this, and we'll get to that. All right, so each of these values represent our best guess at what the profit is going to be for any marketing budget. So if I take my marketing budget of 8, my best guess for the profit is going to be around $2,000, give or take. And note that I had a marketing budget that was around 8,000, and it was had a much lower profit. So my best guess here is wrong, but this line represents my best guess on average across all of the data values. So this is a single line for everybody and represents Y hat, my best guess for every person's data value. Best guess of what? Well, in the concept or in the context, we're assuming we have our independent variable and we're guessing what the dependent variable would be. So I'm assuming that I get a marketing budget and I'm going to guess what is the profit margin going to be for that marketing budget. So we know, again, with real data, our prediction of the profit margin is never going to be perfect. And so here I've added blue lines to represent all of the different ways that this isn't perfect. So here for this dot is 0.91, so about $1,000 more than what I would have predicted with a marketing budget of $6,500. For my marketing budget of $7,000, the actual profit was about $1,200 less than what I would have predicted using my equation. So for each data point, there's an error amount associated with it. So if this is the population line, we denote this error with epsilon. If this is the sample line, which is what it's going to be for us, we're never going to have population data, so this will always be the sample line. Each of these will be the residuals and be denoted with an E. And so that's our graph. That's kind of what's going on here in this situation. That's how we're visualizing this piece. All right. So again, we mentioned this idea of a best line, and how we were going to do it using the ordinary least squares method. So essentially, we're going to take all of those observed error terms, we're going to square them, and we're going to add them up. And we're going to define the best line to be the one that minimizes those squared errors. That's the ordinary least squares approach, or a definition of best line. So how do we do this? Well, there's a couple of different approaches we could take. A bit of a machine learning approach is to calculate just 1,000 different lines and figure out which one has the smallest squared residuals. Now, this is never going to give us the perfect line mathematically. It's just going to give us, hopefully, a close approximation. This isn't necessarily a bad approach. And actually, in a case where we have no background knowledge, this might be the best approach. But because we have a little bit of background knowledge here, we can use a little bit of math to do two things. This will come up with the exact equation that does this, and I'm not going to have to fit 1,000 lines, calculate the distance between each data point and each of those 1,000 lines. So I'm going to get like 10,000 distances, and then square all of those, and then add them all up, and then figure out which of the 1,000 lines is. It's going to save a lot on computation. So while the fit 1,000 lines approach legitimately can give a reasonable guess, the ability to actually calculate this using math saves a ton of time and provides more accuracy. So we prefer the calculated solution when possible. And I say this because while it may be intimidating to do math or calculus, it is it can be faster. It can be a lot faster in some cases, and it is more accurate. Now, I will say, what are we actually doing here in the math? Well, the math is finding the minimum of the difference, or the distance between y hat. Remember, this is our predicted line. So when you see y hat, think of the line's best guess value for a data point. And when you see y, think of the actual value for the data point. So the actual value for the data point minus our line's best guess value for the data point. And remember, those were different. Our line didn't perfectly predict each data point. This is called the residual, or the error, depending on the context. And so we'll eventually denote this just E for the residual, or epsilon if we're doing population values, which we rarely will be, but just to cover that base. But yeah, we'll typically denote this E. And again, when you see y hat, just think this is the y value that we're predicting based on the line. So the difference between the observed y value and the predicted y value, we're going to square up all those errors or differences between what actually happened and what we predicted. These are errors in like a literal sense, right? I predicted something and I was wrong. So this is how far off was I? I square off how far off I am for all the data points. And then I want to minimize that. I want to find the slope and intercept that give me the predicted line. So slope and intercept go into this predicted line. I want to find the slope and intercept that minimize this error term. All right. So the best part about all this is if I fit 1,000 lines and then I got a new data point, I'd have to refit 1,000 lines every single time I have a new data set. The cool part about the math is if I solve the math once, I don't have to redo it. I'm done. The math is ready to go, and I can use it for any new data situations I come across. So I can just use the same math over and over again. So the solution to the calculus, if I do this in the general form, essentially gives me a simple formula for the slope and intercept that we can use in every single data situation. And again, if I fit 1,000 lines, it's pretty cool and computers can do it, but I'd have to redo it every single time. Again, it just takes a lot more time, all for a less accurate answer. It's not really an alternative, to be 100% honest. I shouldn't say that. It is, yeah, it's not really, nobody does that for simple linear regression. Can it be done? Yes, but nobody really does that for simple linear regression. We all use the formula because it's quick and accurate. Now, I will say the answer in the calculus equation, we look at in two forms. We look at for the slope part and we look at for the intercept part. And both of these are going to have a different equation. We'll tend to do the slope one first and then the intercept, and you'll see why in a second. So because we're going to end up doing these calculations for the slope and intercept with sample data, we're going to call these our sample slope and intercept. If you ever had population data, that will give you the population slope and intercept for the rest of this course, not just this lecture set, but this course. We're not going to have access to population data, so this will all be sample stuff. All right, so what are these simple formulas? Well, let's look at them. So for the slope, this is our formula. And again, I'm using the notation B1 to represent the sample slope. And for the intercept, this is our formula. I'm using the notation B0 to represent the sample intercept. Let me note, why do we do the intercept second, or why do I recommend calculating the intercept second? Well, it's because the intercept actually requires us to know the slope to be able to find the intercept. So we need the slope value in the intercept formula. I'll note that the components in both of these equations are the same as we had in correlations. And in fact, that slope equation is very, very close to our correlation. You'll note the numerator is the exact same, and the denominator, all we did was we lost the sum of y minus y bar squared and then the square root. So we actually took out a couple of pieces in the denominator. So this is easier. I mentioned at the beginning of this lecture video, one of the things about regression that's nice is not only does it give you some more detailed information and preserve the information that you can get from correlation, but it's also a little bit easier to calculate. And this is a way that that happens. So because of this, we can, if we're looking to do this calculation by hand, use that same table that we did for the correlation to calculate this. Now, I will say, as we jump into some examples in a minute here, I'm probably not going to re-display the tables and stuff. So go back to the correlation if you want to see all those tables for the different examples as we rework through them. Part of the reason why is, typically you would kind of do all these at the same time. And B, it's just a lot. It would be a lot to add on to these videos, which are already long, and this is already a long lecture set. That doesn't mean that work is unimportant, and that doesn't mean that I don't want you to look at it. So if you feel the need, please do revisit those tables to get a feel for where those come from, while remembering at the same time that you can do all this in software in a much more quick and efficient way than calculating this by hand. I will, though, kind of reference that, hey, we used that and pull the values from them. All right, so the final product, well, we plug in our numbers, we get this sample slope and the sample intercept, and then we put it in this form. So I have y hat sub I equals b0 plus b1 times x sub I. Essentially what this is the predicted y. Remember, that's the height of the line. That's our predicted value for every data point, is the sample intercept where it crosses the y-axis, plus the sample slope, how steep the line is, times x. So y hat sub I, or y sub I hat, is the predicted outcome. And again, when you hear predicted outcome, think, if I'm looking on the line, how high was the line for the x value? That's what I mean by predicted outcome. B0 is the estimated intercept. That's the intercept. We looked at the sample and we made our best guess for the intercept. That's B0. And B1 is the estimated slope. I use data to calculate what is the best slope for this data to go through all of the data points. So intercept's like your starting place, and slope is like your line going through that. I will note in this equation that there's no error. And again, it's because on the left-hand side of the equation, I'm not solving for the actual data point. I'm just asking what is my best guess on the line. So this line equation on the right-hand side, B0 plus B1 times X, that is the exact predicted value. On the left side, the predicted Y. That is the exact predicted value for what I'm predicting. Does that mean that that's equal to Y without a hat? Is that equal to the observed value? No. So when we talk about Y without a hat, that's when we have to account for error, because my prediction's not going to be perfect. But when I'm just saying, hey, this is what I'm using for prediction, there's no real error term here, because I'm just saying, look, this is how I'm predicting it. And again, it could be wrong, but right now in this equation, this is the equation for the line. So no error in the line. I'm exactly predicting what I'm predicting in my line. It's only once I start comparing to real data, that is Y's without a hat, that I may have error. All right, so we are going to jump into some examples in a second, but before that, I really want to talk about the interpretations of these things. So there are standard interpretations for slope and intercept. But being real for a second, the standard Statsy interpretations are almost useless when you're trying to explain this to someone or when you're trying to use this for a decision. So I would view these more as starting places for a real interpretation. And I'll say one of the complexities with providing information as to how to interpret these in a real way is that these are very, very context dependent. Not just in like the textbook context. Oh, you're looking at a marketing budget and a profit margin. I mean, that definitely, but like context dependent in the deeper context of the company. What risk is associated with this? What staffing time? Are people's jobs on the line? All of that kind of stuff comes into play in terms of how we address this, how we look at this, what's good, what's bad, what's ugly. And that's really, really hard to simulate in a course setting. In any case, we're going to go beyond the standard interpretation, so we'll give you something better than that. But realize the context plays a role in this too. And we will talk a little bit about that, but while acknowledging the limitations of a class discussion. So as we mentioned, B0 is the intercept. So the Statsy, mathy notation is the intercept is where the line crosses the y-axis. Now, if you think about where's the y-axis, on the x-axis, the y-axis appears when x is equal to 0, okay? So if we're talking about the line when it crosses the y-axis, that's the same thing as saying the line when x equals to 0. So the intercept, while it is where the line crosses the y-axis, is typically interpreted as, remember, our goal is to predict y given x. So what is the value of y when x is 0? So if x equals 0 means something, if that's useful, then this is a fantastic quantity. You know, what's the value of the profit I'm going to make if I don't have any marketing budget at all? Marketing budget equals $0. That might be very, very, very useful to do. But there's some cases that just doesn't make any sense at all. So for instance, if I'm trying to predict someone's weight given their height, the y-intercept, or the intercept in our equation, would be their predicted weight when their height is 0. And again, that's just nonsensical, right? The idea of a height or x value being 0 just doesn't make sense. In that case, where it just logically doesn't make sense to do an interpretation at x equals 0, think the height equation more than the marketing. Could there be a marketing budget of 0? Potentially. Though if your company doesn't look at that, and if that's ridiculous, then of course pitch that idea out. You're in the height example. We'd never have a marketing budget of 0. But like the height, it's mathematically impossible. It's just a silly question. So one thing that we can do to maintain intercept interpretability in that case is use a process called centering. And we'll talk about that in a moment. That's a bit of an aside here, but that does help to maintain the interpretability of the intercept. I will say when interpreting the intercept is typically not interpreted. Like a lot of, we'll talk about some of this stuff. We'll talk about testing, etc. But the intercept stuff, we typically don't look much at the intercept in regression problems. Far more of what we look at is the slope. So remember, B1 is the sample value, sample estimate for the slope. So the slope is essentially the average expected predicted increase in Y. And note that this is in whatever units Y is in. So if Y is in dollars, say profit in dollars or thousands of dollars or whatever, then that's going to be the units for this slope term. And that's going to be when X increases by 1. Now, I want you to think about, if we're talking about marketing budget, this is the predicted increase in profit when marketing budget goes up by 1. Now, that might not be useful, but here's a tip. If you're doing simple linear regression, you can always multiply both of these numbers and it works out okay. So let's say I don't want to look at the increased profit when marketing budget goes up by 1. I want to look at the increased profit when marketing budget goes up by 1,000. What I would do is multiply the slope by 1,000 and multiply this X increase by 1 by 1,000. So now X increased by 1,000 and this new beta 1 times 1,000 is what I would expect the profit to increase when my marketing budget goes up by 1,000. So that's a handy trick if you ever need to do that. In any case, again, essentially, we're going up and up and up as X increases, or down and down and down. So I say expected increase, but this could be an expected decrease too if the relationship is negative. So when X goes up by 1 unit, what is the average units that Y goes up or down in the data set? Note I'm saying average / expected / predicted. You'll see any or all of these, but average just meaning this is averaged over across the entire data set. So this isn't for like a couple of values. Essentially, we look at the increase, and again, we find this for all of the data simultaneously and look at the average across all of the data values in our sample data set. So that's why I say the average increase in Y when X goes up by 1. It's not really talking about any individual case. It's talking about on average over the whole sample data set. Now, I'll say even these interpretations are pretty, standardized here. I hope the conversation and context kind of help explain those, but still they're a bit generic. Better interpretations for concepts like this are going to include things like the names of the variables and their units. So for example, instead of the average increase in Y when X increases by 1, or let's say beta 0 was 3.42, we'd say, oh, Y on average increases by 3.42 every time X increases by 1. Instead, we'd use the names and units of the variables we're talking about. So we'd say, well, you could expect a $3.42 increase. Note that uses the units in profit, the variable name, as opposed to in Y. For every additional dollar, again, using the units of X, spent in marketing, using the variable name for X instead of the letter X. And again, that's much, much more interpretable and much more actionable. If I go to a boss, say, yeah, Y increases by 3.42 on average for every unit increase in X, they're going to ask what planet I come from. But if I say, yeah, we expect a $3.42 increase in profit for every additional dollar spent in marketing, really? And then I can say things like, if I use my multiply by 1,000 trick, boss, if we put $1,000 in marketing, our data suggests we could get a $3,420 return in profit. Wow, really? Well, maybe we should have that conversation. Now, again, this is the interpretation from regression. We do need to be a little bit careful here, right? Because I'm saying essentially in that claim, I'm implying that if we do this, that will happen, right? That's implying that the marketing budget causes the additional profit. And remember, correlation is not causation. The fact that there's a relationship doesn't necessarily imply they're causal. It would depend on where these numbers come from. So when I say a lot of additional context is important for proper interpretation, that's part of it too. Now, I mentioned with the equations, remember we had the y equals b0 plus b1x. With those equations, we can also replace x and y with their variable names to make the equations a little bit more readable. I'll be honest, in graduate school, I didn't know you could really do this. But after graduate school, I've read a few more applied journals. And in those, they do this all the time. And I've come to quite like it. It makes the equations a little bit more readable and understandable as you're looking at them, and makes the context a little bit cleaner. So that's an available thing too in terms of making the equations interpretable. So I mentioned centering on the previous slide, and there's not really a good place in this course to talk about. We will talk about it in the next lecture set, not the simple linear regression, but when we get to a part of multiple linear regression. But this is as good a point of any as any to talk about it. So centering is the process of taking the independent variable and subtracting its mean value from it for each observation. So I take each observation, subtract the overall mean, and then I get this new number. That new number that I get after subtracting the mean, I use that in place of x in all of my equations. So I essentially update x to now be every x value minus its mean in the regression. What this does is it moves the middle of the data set, the mean, to be 0. And this is kind of fascinating because while this doesn't have any impact, and it has 0 impact on the intercept, this drastically changes the interpretation of the, while this has no effect on the slope, this drastically changes the interpretation of the intercept. So while the interpretation of the intercept was the average value of y when x equals 0, now because x equals 0 is the mean of x, the new interpretation after doing centering is the average value of y when x is at its average value. So in a case of height versus weight, remember the default interpretation was the average weight of someone when their height is 0, which made 0 sense. Now, if we centered height, we would say this is the average weight of someone when they are at an average height. And that's much more interesting to know. It's actually informative. Again, we don't use the intercept or interpret the intercept particularly often, but this at least makes the interpretation, if you're interested in it, something that has a meaning and an application. When do we do this? Well, typically we do this in the case of like height, when x equals 0 is meaningless or nonsensical. So for the case of the marketing budget being 0, well, in a company where that's an option or a consideration, and if I have enough data to support such an interpretation, that is a few cases where I actually analyzed the case where the marketing budget was 0, then I might leave the x value normal. But if the x equals 0 is nonsensical, say in the weight and height example, that's a great candidate for centering the x value and using it in interpretation. Again, remember, this doesn't change the slope at all. It doesn't change the statistical significance test of the slope. All that it does is changes the interpretation of the intercept. I'll mention too, centering is an important thing to be familiar with. With centering, this is going to come up again in a later chapter. It's going to come up for a somewhat different reason, but in the next lecture set in multiple linear regression, we are going to revisit centering, and it's going to be the solution to another, maybe more difficult problem. So it's a good thing to remember because it'll pop back up again later. All right, well, let's try one of these out. So I'm going to use the marketing profit example. And again, I'm not going to re-provide all the data and tables and stuff. If you want that, this is going to be the same data and tables from the correlation example. So go back in your notes, maybe flip back, or on the PDF, kind of screenshot or take a picture with your phone or something if you want to see this, and pull that up. What I'm going to do here is use the pieces that we already calculated from the tables that we already made to build my simple regression. Note that the difference here is I don't just want to look at the relationship. I want to look at more details about the relationship. Not just is a linear relationship there, but what is the nature of the linear relationship? I want to see not just is profit related to marketing, but how much profit increases for every additional amount of money I put into marketing. For this type of study, I'm going to use regression because that's what's going to tell me this information. And again, what do I need from this? Well, for my intercept equation, I need the mean of x and y. And for my slope equation, I need x minus x bar, y minus y bar, and then x minus x bar quantity squared. And I apologize, it looks like I have a typo there. That should be x minus x bar and y minus y bar, not x plus x bar or x plus or y plus y bar. And this should sound familiar. In this, clearly, this is very, very, very close to what we had for correlation. And again, rather than doing the table here, I'm just going to use what we already found. And we already found both of these quantities when doing the correlation. If you want to see how I did that, please, please, please feel free to go back and check out those previous videos, and you can see where this came from. But for me, again, I'm just going to pull the sum of x minus x bar times y minus y bar, and the sum of x minus x bar quantity squared. Two things that I found in that previous table in the correlation section. The numbers from the last section were 9.5 and 15.51, and they're going to give me a slope of 0.6125. I also had the mean of y and the mean of x, and can plug that along with the slope value into the equation for the intercept to get my intercept for this particular regression to be negative 2.7683. So our best fit line, if I plug this into my y hat, and again, y hat just means my best guess, essentially the line's guess for each data point, is y hat sub I equals the beta 0, the intercept, negative 2.7683 plus 0.6125 times x1. Now, remember, x and y are a bit arbitrary or don't give very much information. So you can also include, in this case, the actual variable information here, and that might be useful. So for the variable information, instead of y, I could include profit, and instead of x, I could include marketing. So for these, that would say my predicted profit, my best guess at profit, is negative 2.7683 plus 0.6125 times my marketing budget. All right. So if I want to put this on a graph with my data, this is what that line looks like. And again, think about this. The line is the predicted profit. So this equation at the top is the equation for the line. And what I'm saying by predicted profit is the height that I'm predicting for any data point based on my marketing value. This line represents all of the predictions I'd make. So if I want to look at it for a predicted marketing budget of 10, this is where that falls, for a predicted marketing budget of 8, but also for predicted marketing budgets all throughout. This would be my predicted profits. All right, well, let's practice interpreting this. So remember that profit and marketing are in thousands of dollars. So my equation, as we discussed before, now that we're thinking in thousands of dollars, is the predicted profit is negative a loss of $2,768.30 plus $612.50 for every $1,000 spent on marketing. So for B0, the y-intercept, remember this is if we spent no money on marketing, what the expected profit would be. Well, if we spent no money on marketing, we'd expect to not have a profit. In fact, in this case, we'd expect to have a loss of over $2,700. B1 is, based on the sample, the predicted slope. That is the predicted increase in profit for every increase in marketing budget. So for every $1,000 we spend on marketing, we expect or predict, on average, our profit is going to increase by over $600 for every $1,000 we spend on marketing. So it's important to remember, while these are useful pieces of information, this is only one part of broader logical arguments as it relates to what should we spend on marketing. How should we market things? Should we be marketing in the first place? If we wanted to expand this, we would consider things like the sampling details or range of data, specific contextual things. And actually, we'll talk about some of these on the next slide, like how do they relate in here. But these are the kinds of things that we would look at to provide an expanded definition. So again, I'm going to do that for this example. I'm not going to do that for all the examples because, again, there's just a lot of conjecture. There's a lot of opinion that goes into this. And that's important to just acknowledge that when we talk about all of the contextual factors that relate, these are no longer mathematically optimized, right? This is the best line that we just found. And that I can guarantee you, based on the sample data, this is the best line. Defining best is the minimum squared errors. This is the mathematical best line. And that's kind of where our math ends. What do you do with that? What does this mean in terms of the problem? Well, the general interpretations, those are also correct. But the implications of those determinations, I mean, those determinations are for the sample. And, we can do tests to determine their applicability to the population. And we'll talk about that in a future video. But what do these mean in terms of practical application? Well, that starts to invite opinion. And so that's one of the other reasons we're not going to talk too much about this. So for sampling details, I mentioned that on the previous slide. Excuse me, I said we're not going to talk about this. We're going to talk about this right now. We're not going to talk about this for every single one. And it's because we get in the realm of conjecture. So let's talk about a couple of different ways the sampling could have happened. It's important to remember for all of our conclusions in statistics, and again, I'm only going to talk about it for this one, but this is true for everything. This is true for all the analyses we've discussed previously in this course, and also true for all of the analyses we will discuss in the future of this course. So for everything, we're making estimates and conclusions about populations, yes, but it's only populations that are represented by the sample. So in the ANOVA chapter, we talked about random selection. How did we pick our sample from the population? And so let's say we randomly selected our sample from everybody in the whole world. Well, in that case, we might start making conclusions about global patterns. And that's completely legitimate in many ways. But if I just picked a random sample of random people standing outside of my latest trip to the grocery store, this isn't going to impact or have implications for, say, Fortune 500 companies, right? So you have to be careful that your sample is representing who you want to make your conclusions about, no matter what context you're in and no matter what study you're doing and no matter what analysis you're conducting. Experimental design doesn't save you here. So even in an experimental design, you have to be careful about this. So for sampling details, if this was a really good sample representing kind of broad scale marketing stuff and broad scale profit strategies and really covered the gamut of all the possible marketing things I'd be looking at, well, I might be a little bit more confident in making conclusions based on this. The other thing that, we really don't talk about very often, but in this case, our sample size is pretty small. Now, if that's the best we got, that's the best we got, but we only had a few observations here. Can we get any more data to provide some conclusions that I feel a little bit more confident about? We'll talk later when we get to confidence intervals more and more about that, and when we get to prediction more and more about that too. But ultimately, more data is going to help me feel a lot more confident in any predictions that I end up making using my regression or any conclusions. Range of data. This is so important in regression and so often forgotten in regression. The range of data essentially says, range refers to on your x-axis how far, or I'm referring to on your x-axis, what is the observations that you saw. So for instance, if I only used data, and this is the case in this example, I can't remember the exact numbers, but let's say marketing budgets between $6,000 and $8,000 or $5,000 and $8,000. Well, in that case, I shouldn't make conclusions about, say, the intercept. What happens if I have a marketing budget of 0? Why shouldn't I do that? Well, because I don't have any data. I didn't study that case. And it could be that weird things happen in places where we have a marketing budget of 0. Maybe that's not the case. Or maybe, and you'll see this too, I say as my marketing budget goes up, my profits go up, but maybe it flattens out a bit. And same thing on the bottom. Maybe as my marketing budget goes down, maybe it flattens out a bit. That loss that I'm assuming I'll take is less big than I thought it was, based on just a sample of $6,000 to $8,000 in my marketing budget. Ultimately, what that means is for prediction, we kind of want to stay in or very, very close to the range. Leaving the range of the values that we looked at in the sample when we're doing prediction is something called extrapolation. And depending on who you talk to, it's not that big of a deal or the greatest sin ever. But even in people who think that's not that big of a deal, you do have to be careful about when and how you're doing it. And you should also be aware that you're doing it, that you're a bit stepping outside of a situation that you actually assessed. So really, we feel most confident if our predictions are in a case where we have a lot of data right around that prediction. So if I have a lot of data right around $7,000 of marketing, a little bit above, a little bit below, I feel a lot more confident in predictions that I'm making about the profits that I'm going to see when I have a $7,000 marketing budget, compared to if I have virtually no predictions around that. Even in this data set, you'll see kind of in the middle, there's very few observations in the middle. So extrapolation isn't just being outside of the range in terms of I'm predicting what'll happen if I have $90,000 marketing budget and the highest I had in my sample was $8,000. But it's also, hey, I had 8 and 6, but I had very few at 7, and acknowledging, okay, well, if I do some predictions at 7, I can make, I can believe that that the relationship is linear. But hey, maybe it's not. Maybe something weird is happening at $7,000. Again, maybe at $7,000 it jumps up and then it peaks into 8, or it stays low and then it jumps at 8. And I just don't know unless I have data there. So I am careful about my range of data when I'm thinking about making conclusions. Context specific. So I want to be careful as we talk about some different contexts here, because it's important to realize that there's just a wide range of different contexts that we can look at. So I wrote a couple of these down. I'm glancing at this now. So let's say like net versus gross profit, right? So I'm saying, as I spend, and if you look at the previous slides, as I spend an additional $1,000 in marketing, I get $600 in profit. Well, is that profit after accounting for the money that I spent marketing or not? Because if that's profit not accounting for the marketing money, then I'm essentially giving away $1,000 to only get $600 back. And while starting at negative profit was bad, for every additional money that I'm spending, I'm actually losing more and more and more profit. Or vice versa. Maybe that is after accounting for marketing. And my point here is not to interpret this overly for that one situation. My point is to describe what is some additional context information that can become important here. So for instance, again, if that is, say, the profit before accounting for marketing, maybe I want to be really, really, really careful, because maybe this $600 a month profit, or $600 per time unit profit that I'm anticipating to see, maybe that's terrible when compared to I had to put in $1,000 to get that, versus a $600 profit above and beyond what I spent marketing. Maybe that's fantastic, and I want to spend as much as I can on marketing, or as much as I reasonably can support on marketing, to maximize that flow. And again, I wouldn't then spend $100,000 on marketing without additional data, because we just don't know what that return is going to look like. Does it even off? Does it spike up? Does it spike down? We don't know. We didn't look at that situation. So the range of data comes into that too. Another thing would be break-even point. This is kind of interesting. So like, at what point do I hit zero? Now, this isn't something we're going to cover in regular regression, but let's assume the profit is above and beyond what I spent marketing. And remember, if I have zero marketing, I'm losing money. So one question that might be of use to a potential employer is how much do we have to spend on marketing on average to break even so that we're not losing money? And that's a cool analysis. It's not something that we'll talk about specifically in this course, but you can use the equation pretty easily to do this. Essentially, what you would want to do is say, how high does marketing have to be for my profit to be 0. So you would set this to 0, and marketing would be your question mark, fill in the blank, and then you would do a little bit of math, plus this on both sides and divided by that on both sides to calculate what do you have to spend on marketing to end up with a 0 profit, to end up breaking even. So there's a couple of different things that you could look at here. It is important to say that while there's a lot of important considerations, there's a lot of right answers in terms of context-specific interpretation, there's a lot of wrong answers too. So just because something takes into account context in the interpretation of an equation, that doesn't mean that it did so correctly. So be careful. With that said, this context-specific interpretation is really important for getting practical insights from all of your statistical models, but something like this regression model specifically. One last thing that I'll just mention here is the consistency of the effect. Like, is this just an accident? Is this random? Or is this a really overall consistent effect? And we're going to find that with statistical testing. That's something that we'll check out when we get to our future video on doing not statistics in terms of calculating this, but statistics in terms of doing tests and confidence intervals with these. Last but not least, I'll mention the size of the effect. So for instance, we kind of referenced this earlier, but like maybe the profit margin has to be bigger than something to be worth it. So is the size of the effect worthwhile? There's a couple of ways to look at the sizes of effects and determining that. I'll say with our statistical testing in a hypothesis test, we determine if something is significantly different than some null hypothesized point value, typically 0. But just determining that something, there's enough evidence to believe that it's not 0 does not necessarily mean that it's of a useful amount. So the size of the effect is a completely different determination than the statistical significance, and sometimes you'll hear this called practical significance. Okay, yeah, it was statistically significant, and that's a precursor, that's a necessity to discuss practical significance. There is no practical significance without statistical significance. We have to be confident that this is a pattern that's due to more than just chance. But after we establish that, we can discuss practical significance. That is this something that's worth acting upon? Is this big enough to be worth it? Now, that worth it question, that's not a statistical question, not in a remote sense. You can talk about numbers, but at that point, we leave the statistics and start talking about, again, broader contextual stuff that's super important for decision making, but not something that we do in our basic stats and even in advanced stats. Again, when I work with clients, I kind of present this and I shrug my shoulders and say, I don't know if this is worth it for you. You tell me what's worth it for you. And they talk about a ton of things relating to their business in that discussion. Again, some of which are other different statistics, but a lot of just which are priorities. And that's not a statistical discussion. So you can have the worth it conversation and have a bunch of people have a bunch of different opinions, all based on the same statistics, completely legitimately, because each might have their own assessment of what is worth what. It's worth mentioning that there are standardized sizes of effects. Sometimes you'll hear those called effect sizes, and those can be compared to rules of thumb regarding interpretation of what's a big or what's a small effect. But in a practical context, it's much better to interpret using kind of these interpretations that we've discussed in this lecture video, and then compare that to, again, things like worth it in your context. So in an applied business case, I highly recommend not using standardized effect sizes, even though sometimes in research we kind of tend to do that. To me, personally, that's just a bit of a more lazy approach. The last thing that I'll mention with the size of the effects, especially with an eye that in a future video coming up soon, we're going to be talking about confidence intervals, is that when I look at and interpret the size of the effect, typically I do that in the context of a confidence interval, because remember, our best guess for the slope, say, is probably wrong. the confidence interval presents a reasonable range that I expect that to be in. So even though my best guess is probably wrong, I can look at the reasonable range. Now, the interesting part about the interpretation of the confidence interval in an applied context is both sides of the reasonable range may have different interpretations. And if both are reasonable, then I have to be careful about how I look at the situation, acknowledging that both potentially a negative outcome or a positive outcome could happen. The ideal situation is when the confidence interval, both sides tell the same story. We're going to be making more money, whether it's on the low end or the high end of the reasonable range, or we're going to be losing money, whether it's on the low end or the high end of the reasonable range. But for me, when interpreting the size of the effect, I tend to use confidence intervals to guide that interpretation rather than just my best guess at the slope or the point estimate in this case. All right, well, that was a lot on interpretation, so we kind of took a little bit of a detour there, but hopefully very important. And again, we're going to continue to come back to that. Here, though, now you need to revisit how we do these darn calculations to even get that best line regression equation for our data in the first place. So I'm going to give you the context and the data set. Please do not feel like you have to start from scratch. Revisit in your notes where you already built that big table and use the pieces just like I did in my example. In any case, whichever way you try, whether it's rebuilding that table from scratch or going and finding it in your notes and using the pieces to build your regression equation, go on and give a shot to building your regression equation. That is, finding the values for the mathematical best line for this data. It's kind of cool. You're going to find the very best one. It's going to be perfect, mathematically perfect, the best possible line you could have done. So go on and find that line for this situation. After you find that, for hypothetical bonus point, and again, I'm not giving you bonus points in videos, but whatever, for a +1, for a gold star, also try to interpret, try to think through this problem, try to think about it a little bit deeper than maybe you normally do, and get some practice in actually thinking about how might I use this or what might this inform. In any case, go on, give this one a shot, and then pause the video, give this one a shot, and come back. We'll see how you did. All right, let's see how that went. So again, I'm just using values from the previous table. If you redid it, double check. Excuse me. And if you want to see the work, go to the previous table in your notes where we did it before in the correlation lecture. Here for my slope, I have the numerator 363.02, denominator 67.76. And my slope is 5.3574. For my intercept, I have the y bar, the average outcome is 78.9625. The slope we just found, and the x bar 3.9875. Don't get too confused here. Looks like I switched the order of the slope and x bar. So the 3.9875 is this x bar, and of course the slope is at 5.3574 we just found. All right, so looking at this, our best fit line based on this is y hat sub I equals 57.59999 plus 5.3574 times x. And again, the x and y are just kind of arbitrary generic labels. We could plug in some more informative variable labels into this equation to get a better feel for it. The predicted sales is 57,599 plus 5.3574 times the number of students. So if I put that on a graph, this is what that looks like on a graph overlaid with my data points. Very cool. And this does look like it's a pretty close line to all my data points. So let's interpret this. I'm going to assume sales are in thousands of dollars a year and students are in thousands. The null hypothesis is the predicted sales when no students are there. So again, things like intercept is blank doesn't really mean that much, but like $57,500 with no students, yeah, that Makes sense. Now, one thing I want to call out with the intercept, does it make sense that a pizza shop could be doing sales with no students? Yeah, absolutely. Think about the summer. There's no students around. So this number might actually be useful. But I will call out that none of the data points in the sample looked at a case with 0 or very low numbers of students. So though the intercept is a reasonable value, that is, I might not need to recenter my X value students in this case, it's outside of the range, so I'm extrapolating a little bit, and I might want to be careful about that. All right, so for the slope, this is the 5.374, 3574. This indicates that for each additional 1,000 students, that is for each unit of X, I expect, or on average, or I predict that there will be additional $5,000 per year in sales. And again, what's that number? 5,357. This is a guess. It's not wrong. It's my point estimate. It's my best guess. There's a range around that we'll discuss later. What does this paint a picture of? Well, it paints a picture of a business that is making an okay amount of money, depending on what they need to break even, 57 grand, even without students. But with students, you can definitely see a bump in the sales that they're seeing. And again, it's about $5,000 for every 1,000 students. Does this pass a gut check? Yeah, it does. As they get more students, they get more money, but they're still functional without any students. They sell pizza to everybody else in the community too. And so, yeah, there's a lot of things here that could aid in the interpretation. Where is this? Is this across multiple campuses? How are the data collected? What's the product cost? So for instance, all right, you're making $5 for every student you get, or $5 in sales, but are you spending $8 in supplies? Like, that could be useful here to know. So there's a lot of additional information that could be handy to interpret based on the situation, but our basic interpretation is still pretty useful and a great starting place for diving deeper. Ooh. All right, ladies and gentlemen. Well, thanks for sticking with me through this one. In this video, we talked about simple linear regression. We kind of talked about what we were doing with simple linear regression, the idea behind it. Then we talked about how to fit some simple linear regression models. We talked about calculating the best slope and the best intercept, and then as importantly, or more importantly, how we can interpret those things in some different contexts. We worked through a couple of different problems. And yeah, that took us to now. So again, this was a long one, but ladies and gents, thank you so much for sticking with me through this video. I appreciate it, and I will look forward to catching you in the next one.